G'day, in this video we're going to be unpacking the concept of torque. This video covers syllabus content 5.2.5. It's our final dot point on circular motion. And in this one we're going to be investigating the relationship between the rotation of mechanical systems and the applied torque. So our key learning intentions today are to first define torque, then calculate torque in perpendicular and non-perpendicular scenarios. So first, what is torque? Essentially, we can describe torque sort of as a turning force on a rotating object. It helps to describe the kind of force which is being placed on objects that results in some sort of circular motion. It's really important to know that torque is a vector quantity, meaning that it does not just have a magnitude, but also has a direction. For there to be some sort of torque, generally speaking, there is some sort of pivot for which an object is able to turn about. In this example, it's the hinge on the door. And then we have some kind of lever from which a force can be applied to make the object turn on the pivot. Now, because torque is a vector quantity, it means that we need to give it some sort of direction. Torque is an interesting one because it doesn't necessarily match the direction of rotation or the direction of motion, just like most vectors usually do. What we use is the right hand grip rule. Essentially, if you curl your fingers to make a gripping shape and point your thumb directly upwards, and you match your finger direction with the direction of rotation, your thumb will point in the direction of the torque vector. So for example, in figure 1 with our opening door, if you were to hold your right hand out and have your fingers from the base of your hand to your fingertips follow the rotating motion of the door here, you would find that your thumb points in the upward direction, meaning that for this diagram, the direction of the torque vector would essentially be out of the page. Now, torque is defined as radius times perpendicular force, or radius times force sine theta. Radius is obviously measured in meters and perpendicular force is measured in newtons. Therefore, we get a measurement for torque in newton meters. This may be a set of units of measurement that you are possibly familiar with, especially when looking at work. Work can be defined as newton meters as well. We usually define work as an energy in joules. However, torque does not follow this same convention. We never show torque in joules. And the reason is that, as we talked about before, torque is a vector quantity, not scalar. Energy is scalar. Therefore, scalar measurements can be expressed in joules. Vector quantities like torque cannot. Now, the diagram on the left gives you a pretty good indication of what we're looking for when calculating for torque. We need a radius between where the pivot is and where the applied force is, as well as a force which is perpendicular to this radius or perpendicular to the lever. Multiplying these two numbers together will give you your torque in newton meters. However, we don't always apply forces perpendicular to the lever and or the radius. In this example here, we can see that the applied force is slightly inwards towards the center of the circle. If this is the case, the amount of force which is being applied in the perpendicular direction will be less than the total amount of force which is being applied on the object. We can apply some right-angled trig to get our value here, force times sine theta. In the diagram, I've essentially broken up my force vector into components. We have F parallel, which is parallel to the radius and the lever, as well as F perpendicular, which is perpendicular to the lever itself. This value is what we care about when calculating for torque. Given that F parallel and radius are parallel to each other, we can find here that theta and theta are going to be equal to each other because they are alternate angles. Given that we have a right-angled triangle with angle theta, we can determine that sine of theta is going to be equal to opposite over hypotenuse, which in this case is F perpendicular on F, meaning that F perpendicular is simply equal to F on times sine theta, which is the term that we find in our alternate equation for torque. In the practice question for this video, we have a spanner with a handle 42 centimeters long that's being used to tighten a bolt on a bike wheel. First off, we're going to calculate the torque if 35 newtons of force is applied perpendicular to the handle, and then calculate for the magnitude of force required to produce the same amount of torque, however, assuming that the applied force is an angle of 50 degrees to the spanner. Now, the first thing that I'm going to do for A is draw out a diagram and extract any key information from the question. Now, because this force is perpendicular, we can sub straight into our torque equation. So torque, which is the Greek letter tau, T-A-U, is equal to radius times perpendicular force, which is equal to 0.42 meters times 35 newtons. This gives us 14.7 newton meters, which is 15 newton meters to two significant figures. Now, B is slightly more complex, so again, I'm going to draw a quick diagram and extract data into a data column. Because we have an applied force at an angle in this question, we need to use the formula torque being equal to radius times force sine theta. What we can then do is rearrange for force, substitute, and solve. What we find is that this new force required is 47 newtons, again to two significant figures. What this tells us is if we don't push on an object perpendicular to the lever, if we're trying to get some sort of torque going, we're going to need more force to be able to generate that same torque. Thank you very much, everyone. In the next video, we're going to be moving on to the third and final inquiry question for Module 5 Advanced Mechanics. This one focuses heaps on gravity and objects in space. So we'll start by learning about Newton's law of gravitation. But until then, have a good one.